All right. Good day, everyone. Welcome to our webinar today titled Mineral Innovation Through Mineral Exploration. My name is Georgia Tamuso. I am currently in my fourth year studying applied geophysics at the Federal University of Technology, Akure, and I'm also currently serving as the president of the Society of Exploration Geophysics, FUTA. I am delighted to introduce our speaker today, Kenneth Moya Gabo. He is PhD candidate in geophysics at the University of Witwatersrand. He's in seismic solutions and techniques for mineral exploration, designing and conducting innovative and cost-effective in-mine seismic experiments for mineral exploration in the Bushveld complex, sensing technologies such as wireless recorders, and seismic land streamers to acquire seismic data on surface and inside mine tunnels. He also served as a Semeradi research intern at Mandela Mining Project under the Advanced Ore Body Knowledge Program. He gained knowledge of the mining industry and he obtained theories in CRT and thermal screening. So I'd like to pass the mic to you now.
Oh, thank you, Roger. Let me just share my screen quickly just now. I'm gonna.
Okay, but before that, I would like to do a little housekeeping. Please type into the chat.
In progress.
Sure, if you guys can see my screen now. Can you see my screen now? Hello.
Hey. Yes, can I see your screen? Thank you.
Oh, okay. I don't know. My computer somehow decided to start being slow now. All right. Yeah, thanks everyone for joining. As Rudyard has already introduced me, my name is Kenneth, and I'm a PhD candidate at the University of the Witwatersrand in South Africa. And today I'll be just giving you a brief of some of the work we've done in the Bushveld complex over the past 2-3 years. So this will be looking at mineral exploration solution, and these case studies are based in the Bushveld complex, as I've mentioned. So firstly, I would like to talk about the Vet Seismic Research Center, which is a center that focuses on research, innovation, and action, where we are trying to get new technologies that can also be cost effective and as efficient as possible, and also looking at some legacy data, reprocessing of seismic data, and also working on acquiring new data set over time and processing that, and making sure that all these tools are environmentally friendly and can be able to work in unconventional and any conventional environments. So we know that there is a growing need for minerals and these rare minerals that are going up over the years. And who doesn't need some of these minerals based on the fact that there are more advanced technology increasing over time. There are computers and phones being built over time that we need to extract these minerals and be able to use them over time. So the mining industry then is now put under pressure to then produce more of these minerals and for our development. And platinum, as we know, for example, is used in more than 20% of all the manufactured goods. And there has been a growing need over the past few years, and it is expected that it will at least quadruple by 2040. And also the whole need for going green, having green energy is also an impact towards us looking for these minerals and exploring for these minerals in a more cost-effective and environmentally friendly way. So the motivation behind this is the fact that mineral exploration focus has increasingly turned to search for economically feasible deep-seated mineral deposits. As we know, in South Africa, we have our the surface minerals that we have exploited most of them, and we are left with going deeper and deeper. But we have brownfields that already exist, where 60% of the precious metals discoveries have been made for the past since 1996 and 2008 are linked to historic mines, meaning that we can continue mining these brownfields. We can also move into green fields, but brownfields are contributing more to these precious metal discoveries. So the problem that we have with working in brownfields is the fact that we are going to encounter infrastructure on surface, which we all know that our geophysical methods are very sensitive to noise. It can be electrical noise, it can be vibrations from trucks, from crushers blasting and drilling, or electrical noise from high voltage power lines or large number of trucks and whatsoever. So this causes us to then look into how do we then collect seismic or any geophysical data in such noisy environments. So this has called for us to ask certain questions, whether could underground spaces, for example, be utilized for cost-effective exploration and mine planning? Could the existing geophysical instruments, for example, be able to record anything in highly noisy environment or on surface, for example, or in underground environments where you are unable to have any GPS? Will you be able to then tie your data with any surface data? And also the logistics of collecting seismic data in such busy environments, for example, taking equipment underground or taking equipment into a mining area, that can be a bit challenging. So those are some of the questions that we're asking in terms of, can we be able to collect seismic data in such environments? So we set out to design such seismic experiments. Mainly we focus on seismic experiments as it has a higher resolution compared to the other geophysical methods. So we developed this seismic solution for deep mineral exploration, incorporating various sensing technology and improve some of the signal penetration to our depth of target. As we move closer to the target, we'll be able to at least resolve it much better. So some of this work that I'm presenting now has been published in the early, in January of this year. So I will just go straight into looking at the case studies that we have. I'll start with one case study where we're looking at where we collecting seismic data in underground tunnels, and then we'll move to case study 2 where we collected seismic data in an open pit mine using different geophysical methods, and we look at all the different types of ways that we've used in both different settings and some of the issues we encountered in this area. So the first section I'll be taking you guys on is the in-mine seismic studies that we have conducted in 2020. We started by conducting 2D in-mine seismic surveys at this site 1 in the Bushveld complex to characterize geological structures using the different seismic data acquisition techniques. This involved the use of LiDAR, ERT, which is electrical resistivity tomography, GPR, and seismics. But the focus of this talk will be on the different seismic data acquisition techniques that we have used to image the geological structures and potentially the ore body. While GPR and ERT were used to map the tunnel roofs and sidewalls, and this information was used to assess the stability of your hanging wall and your sidewall to mitigate any fall of grounds due to the unstable hanging walls, as I've mentioned. So site 1 is located on the south western limb of the Bushveld complex in the Pashuk section. The mine is currently under care and maintenance since 2017 due to economic reasons, and is currently being used to test new mining technology. It's currently used to test new mining technology, making it an ideal site for a field research that we are trying to undertake. So the 2 economic horizons found in the mafic, ultramafic comminate rocks of the complex are the Marinsky Reef and the UG2. Sorry, it stopped sharing. Rodiat? Okay. It stopped sharing and it says I can't share anymore. The host disabled that times.
Kenneth, I think they need to give you host rights. What I can
Yes.
see, I think you've been removed from there.
Yeah, I think I just noticed that, so I'm trying to get hold of her. I don't know whether she got kicked out or what, because she's not responding. $75 Ola Jide. I can see you saying something I can't hear. Yeah, I think the account for SCG has locked off. So I think maybe she had internet issues.
What about the demi?
Yeah, there's
like
Demi
D?
host, who's the host. So I don't know who that is.
Well, they're supposed to assign you.
Yeah. Oh, okay. There you go. I'm a host now. So yes, we can continue again. Sorry about that. As I was saying, so we have the two economic horizons are found in the mafic to ultramafic cumulate rocks, the Rustenburg clayite suit, and the two horizons are the Marinsky Reef and the UG2, and are mined at an average depth of about 500 meters below the surface, and the UG2 occurs about 15 to 400 meters below the Marinsky Reef in this site. So our aim on this in-mine seismic solution, as I've already mentioned, is to test if we could collect seismic data in GPS denied environments, or could these underground spaces or tunnels be used to acquire cost-effective seismic data for exploration and mine planning purposes? And can we also, with the fact that there is noise underground and it's a bit challenging to get the equipment underground, will we be able to overpass these challenges? So a bit about seismic principle. So what we would do is to have a conventional way is to place your sensors, which are your receiver stations, on the surface, and have your source. Your source can be in a form of a vibrosize, it can be an impact source, or it can be an explosion of some sort. And for example, here on the picture, it's a vibrosize which creates a sweep over time, and as it sweeps, you will have seismic waves traveling through the different mediums. You have your targets with different geophysical properties, and these geophysical properties are going to be useful for you in order for you to image any target that you are looking for. These factors that affect your seismic response, for example, as I've mentioned, physical properties, you'll have density and velocity, their fractures and their orientation. The depth of penetration is also something that will affect your seismic response, the geometry of your target, whether it's vertical or horizontal. The thickness of your target also, will you be able to image, resolve, or only detect that target, and the different lithologies that you have over below your surface, will you be able to have a good acoustic impedance contrast, on that. So now we look at the different sensors that we have that are available for us to use. On surface, for example, we usually just plant the geophones, as you see on the image on the far left. On the image on the far left, we have our planted geophones. And then on the middle image, we have our seismic lens streamer where we remove the spike on the planted geophone and put a base plate. And this base plate will be able to help us have good coupling in areas where we are unable to plant the geophones. We also have wireless sensors, which they use the conventional geophones, the planted geophones. You can plant them on the ground, but with them, you can leave them in the field to record over time. You can use them as passive. You can also use them as active sensors. So these are some of the technologies that we have available to use for our experiments. But now, going underground, we will also look into having a lens streamer underground and planting the geophones, but keeping in mind that when you are 500 meters below the surface, you are already on hard rock, while on surface, you might have weathered overburden where you can plant the geophones easily. So it might be a bit difficult for you to plant the geophones underground on hard rock. Also, the lens streamer is a good tool for you to use underground, as it has a base plate that can just sit on the base rock. And also the wireless sensors, you can use the wireless sensors underground. The only thing that you would need to keep in mind is the fact that the underground environment is GPS denied, so you will not be able to get any coordinates or referencing of your wireless sensors. I would also like to put emphasis on the amount of time it takes for one to plant geophones. It took us about 90 minutes to plant about 48 geophones for seismic profiles, while it will take us about 60 minutes to just lay down a lens streamer. And for wireless sensors, you will take about 120 minutes, as you have to connect the geophone to the node. I am emphasizing this because the amount of time you spend collecting your seismic data is going to affect the cost of your survey. So we move on to look at our seismic sources. We start looking at the vibrosize, which will input more energy. You can do roll along easily. It's much faster to use on surface, but you have to consider the fact that you might be working in places where your development tunnels or your stopes are 1 meter high. So it might be a bit difficult for you to, actually it is difficult for you to take the trucks underground for any experiments. There is also an accelerated weight drop that we have, of which you can mount it onto the car on surface and collect seismic data using that. And then we have the conventional way that we usually use, which is using the sledgehammer to collect our seismic data, which is much easier and cost effective, and accessibility to the tunnels is much easier using your sledgehammer, and the logistics to get your sledgehammer into the underground environment is much easier. So using the vibrosize for our experiments is a no-go because we won't be able to get it underground. The accelerated weight drop, due to safety reasons, some of the areas in the mine are inaccessible because of safety reasons. So we decided not to use the accelerated weight drop because of its energy. And we decided to end up utilizing the sledgehammer. So now safety, as I've mentioned, is a bit of a concern as you're working in underground environment. You can imagine you have your development tunnels that are about 0.8 to 1.5 meters in height. So whenever you're swinging the hammer underground, you need to be a bit careful of not hitting the hanging wall or hitting the side wall and having any rock force. So now also on your entry tunnel, your entry tunnels are about 3 to 4 meters in height, of which it's a good height for you to have your seismic tracks or your car drive into the entry tunnel and conduct any survey on the entry tunnel. But sometimes your entry tunnel do not have any ore body below them or any geological structure that you would like to target. But also we kept a methane gas detector with us just in case. As you can see on the video here, when the gentleman hits the plate, there are sparks. So you need to make sure that wherever you're working, you are sure that there is no methane gas that is detected in that area, because that can cause some disaster in that environment. So now this is the basic geology that I've already mentioned, where our target is the Marinsky Reef, and it is coupled by the anorthosites and norites, of which we use those as a proxy to image the economic horizons that we have. I will go in more deeper into, I'll go into detail as we go forward in the presentation. So some of the structures that affect the Bushveld complex, we look at faults. We have dikes that can cross-cut your target, which is your reef. You can have slump structures, potholes that can cause some form of depressions on your reef. Then you have some reef loss, and some of these faults and dikes can act as conduits for methane gas, threatening the safety of the mine workers and also production of the mine. Therefore, I believe there is a need for us to conduct in-mine seismic surveys to better image the structures ahead, below, or on the sides of the tunnels or stopes. And understanding the geometry of the ore body will also save the mines some money and time, as they will be able to plan ahead of time. So our project at Site 1 got split into 2 phases. The first phase involved understanding the physical properties, mainly density and velocity of the rocks that we will be working on, and conduct seismic modeling of planning the position of the seismic lines. So after collecting the rock properties, we head on to conduct 1D synthetic data using the laboratory measurements. We also collected some of the rock properties in underground using our handheld velocity meter. And we then take the geological model and conduct seismic simulations and produce some synthetic shot gathers. So we can see if we have any seismic response, we'll be able to image anything ahead before we can go and acquire the seismic data. So the first thing that you would need to do is to do a site visit. As I've mentioned, that the mining environment is a bit tricky, because you might look at the mine plans and plan to conduct your seismic surveys at different locations and whatsoever. And then when you get into the mine, you find that the stope is probably about 0.8 meters in height, or that place is not declared safe. So you are unable to conduct any surveys at that place. So you do need to go to the site visit and test some of your equipment also. And then for seismic acquisition, you need to test your noise levels, as this is going to affect the processing of your data. and be able to choose which equipment that you're going to use and the different parameters in terms of your recording length, your sampling interval, and whatsoever in terms for the data acquisition. So this, after collecting your data, you'll be able, picking your different parameters will help you in designing the filters to remove some of the noise and produce a seismic data set for interpretation purposes. And then to constrain the data, we used the geological models, the boreholes, and any other information that we had for the interpretation of the data set. So the physical property measurements, as I've already mentioned, you can either take the ultrasonic pulse tester and go underground with it and make direct measurements on the rock, or you can have samples that you bring to the laboratory and conduct physical property measurements, which will be your density and velocity measurements. And then with those, as I've mentioned, we conduct 1D synthetic modeling. We take the velocity measurements and the density measurements, and then we convolve those to get acoustic impedance and reflection coefficients, which in this turn, we utilize the borehole that we had, the one that you see here, where we had the Marinsky Reef marked in red and the UG2 as blue at the bottom here. And we can see by conducting our 1D synthetic modeling, we can see that we are going to have a strong signal caused by the Marinsky Reef package. And we're also going to have a strong another signal that comes from the UG2. So this gives us some confidence as the collection of these physical properties was necessary for us to do this synthetic modeling and help us in terms of seeing if we'll have any seismic response from the two target horizons. So we move on to do 2D synthetic model, where we take the borehole information and we build we take the borehole information and geological reports from the mine to build a 2D acoustic model and conduct 2D acoustic finite difference modeling to investigate the seismic reflectivity of the mineralization and constrain the seismic interpretations. The thickness of our Marinsky Reef in this study area was about 0.63 meters, while the UG2 is about 0.84. And they have an average dip of 7 to 10 degrees. And the area, since it has faulting and some dike cross-cutting some of the regions, so which is why we have inputted a dike and a fault in our model. And modeling of the tunnel is conducted with the assumption that the free space on top here represents the air, which will be our tunnel floor here, where we put our geophones. The synthetic parameters of this model were kept the same as the acquisition parameters of the collected data in order to be able to constrain the two data sets. So this just shows you some of the wave modeling that you can have, the P wave field and the S wave field that propagates through the different lithological boundaries. So to substantiate the accuracy and cost effectiveness of using combined passive and active seismic techniques for subsurface characterization and use the velocity model obtained from this passive data. and refraction seismics also that we collect on surface to improve our static corrections. We collected seismic data on surface in order to do that, to produce velocity models that will help us in improving our static corrections and do velocity analysis in reflection seismics workflow. So then, as I've mentioned, that we've collected some data on surface. We collected passive seismic data with continuous recording with 3 broadband seismometers that were collecting data for about 5 to 7 days. This data was used to create velocity models that I've already mentioned that will utilize for static corrections. So for active seismics, we collected about 5 seismic profiles on surface. We're using the lens streamer and the accelerated weight drop, as there are no safety issues on surface. We used the conventional geophones and also the wireless sensors with profiles that can go up to 245 meters. So going underground, we collected about 7 seismic profiles using the lens streamer. We also had 100 hertz component spiked geophones and 14 hertz geophones that we wanted to test out. Our sledgehammer was the source, as I've already mentioned. We were able to have seismic profiles that range between 26 meters to about 115 meters. I have to emphasize that for this presentation, the focus on the results is on these profiles, P5, P6, and P7. So some of these techniques that we were trying out underground is also to put the lens streamer on the tunnel wall and see if we can be able to record anything in any or image any geological structures within the pillar. So as you can see here, we supported the lens streamer with the roof bores and recorded our seismic data using spiked and also the lens stream. So as I've already mentioned, that we've used the sledgehammer, metal plate, and lens streamer. So for this, as I've mentioned, that we are only going to focus on P5, P6, and P7 data. Here, I'm just showing you the comparison between the raw and the process shot gathers that we have taken through some basic processing, pre-stack processing workflow, where you can see the reflection R2 is appearing up there. And then after processing, it is much clearer. And we did not have reflection R3 on our raw shot gather. A represents raw shot gather, B is processed, C is raw shot gather, and D is our process shot gather. We are able to now see an additional reflection on the process data, which is likely hidden under the ground raw that dominates the data set. So now, combining the borehole and seismic data integration, we received the geological information after we have already collected the data, and matching the borehole data with the seismic data, we can see that there is some minor discrepancies of about 0 to 3 meters, and this of depth of target horizons, and these discrepancies might be due to the fact that the boreholes that we used are projected onto the seismic profiles, and they were not drilled directly on the seismic line. This can result in the interpreted reflections having an apparent dip compared to the borehole data. Therefore, the mismatch is expected on the seismic section and the borehole data. Secondly, I would say the mine ore body models are poorly constrained in areas that are not covered by the borehole data. So the seismic results suggest that faults and dikes cross-cut and displace the Marinsky Reef, the UG2, and an additional reflection which we named R3 horizon, which this constrains their timing of activity. That is, they were active after the reef deposition. I'm referring to the faults and dikes as they cross-cut our Marinsky Reef and our UG2 and R3. And imaging of this structure is important to us for future mine planning at mine site 1, as this indicates areas that may not be mineable because of the loss of ground. And although some of these faults are detected on the seismic section, their throws cannot be determined with confidence, as their displacements, I'm referring to throws, are below the seismic resolution limit of the data. We can only detect the structures. Yes, so I will just also give a bit look of the GPR data that we have collected. The data was collected around the pillar in 4 segments, and this was done to image the structures within the pillar and the roof. As you can see, the 4 segments labeled in green, purple, red, and blue, which were going around the pillar like that, of which you can see some diffractions that come through on the data set, which some of those diffractions can be due to fracturing and some linear structural features that are within the roof wall, and also some of the roof boards that are put into the roof might also give some diffraction events in the GPR data. So now moving to phase 2 of case study 1, to design the new survey. Our aim here is to design the new survey with the target being the dike and the faults that were missed in the previous experiments at the meshed portion of the profiles. So our first phase, we conducted P5 and P7 along this line, but due to us collecting the seismic lines into portions of P5, P6, and P7, we had areas of low fault, and these areas happened to fall on the dike and the fault system that we were interested in, which is why in phase 2, we came and collected a much longer line, T3, that will put the dike and the fractures or the fault in the high fault region. So also when we collected the second phase, we had a drill now where we would be able to drill the conventional geophones, the spiked ones, into the ground, and also have the lens streamer, such that we'll be able to have a comparison between the conventional geophone and the lens streamer into our data set. We also had to keep in mind with the fact that the underground mine environment is quite noisy, as you can hear from the sound on the water pump on the other side that is pumping water out of the mine stove. That is causing vibrations that introduce noise into your data set. So as I've already mentioned, these are some of your sources of noise. As you can see, we just measured background noise here. You can see this data here is just noise, and this can come from ventilation, the flowing of water and water pumps, and some of the equipment can also give you the noise into your data set. So you need to keep in check when you're collecting your seismic data of this type of sources of noise. So we compare the lens streamer and planted geophones. The first image here, which is A, is your lens streamer data set. The second image here is your raw planted geophones. So both A and B are raw, not processed. And you can clearly see there is some disruption of our data set at this region, while our lens streamer is a bit clean in this region. You are still able to see some reflection in the data set that are enhanced more when you process the data. As you can see, the processed lens streamer is much cleaner, where you now can be able to see your first breaks clearly compared to the raw data. And planted geophones also, the data is not lost because of the noise. We can recover some of the reflections if we do thorough processing of that data. So we look at the data set now in terms of the raw and processed data on another line that we collected. And we have some reflections, and this we can see the clear first breaks on our short gathers, and the reflections could they be linked to the UG2 or the Marinsky Reef or the UG1? That is something that we will be investigating. We also tried something different because we already know that underground environments will probably be drilling over time. So what we try to do is record seismic data while having a drill and look at those short gathers and try to do any cross correlation of the data set and see if we can get anything out of that data set. So now looking at the stack sections of our data, of the first line that we collected that was across the development tunnel, we can see some clear reflections that are deeping, and they seem to be cross-cut. It might be fractures and faulting that happens. And also in this far end, there is a dike that cross-cuts the line, of which we interpreted it to be in that location. And then we move on to the longer line that we collected along the development tunnel now, which was to increase the confidence of phase one seismic line that we collected. And we do see some reflections there, which could be the UG2 and some dipping reflections that we are identifying on our seismic sections. And this is still the same line on T3, but it's extended. But now this, we were using the previous line, we were using the lens streamer. And then on this one, we were using the spiked geophone. We still see the dipping reflections, which might be our UG2 or UG1. And then we have a shorter line that we collected, and it shows two clear reflections, which might be our UG2 and UG1, because we do not attribute these reflections to be the Marinsky Reef, since the Marinsky Reef was on the same level as the, you could literally see the Marinsky Reef on the side wall of your tunnels. So any reflections below that could either be the UG2 and UG1. And as I've already mentioned, UG2 averages about 14 to 400 meters below the Marinsky Reef in the Bushveld complex. So now we just took our data set and now start putting it into a 3D view just to have a few of all the data set that we have collected. We have our development tunnels and our incline tunnel. We have all the seismic lines that we have collected over time. And we have conducted P-wave refraction tomographies that show us the velocity regions. We have weak zones that we can identify into our data set. We are able to see the weathered layer on top, which actually, it's not the weathered layer, I would say fractured layer, because we are already underground and on hard rock, so it's fractured layer that has lower velocities compared to the hard rock that goes to about 6,500 meters per second. And then we picked that hard rock, which is about 6,000 to 6,500 meters. And then we also have our base of the fractured rock, which is about 1,000 to 2,500 meters per second in velocity. And then we also put in our seismic sections into the tunnel model, and so that we'll be able to constrain the reflections that we have, and also we would like to depict some of the structures that we believe cross-cut the horizons with some structural interpretation on the data set. We are also planning on integrating the data with the borehole. We only utilized about 2 boreholes for our constraint of this, but with the 2 boreholes that you can see here, the red represents the Mariinsky and the Mariinsky contact, and the blue represents the UG2 contact, of which when we place the Mariinsky reef model and the UG2 model, they actually coincide with some of the reflections that we have seen. So in summary, to the inmine seismic data, the seismic data clearly depicts mineralization and geological structures, and this illustrates the potential for inmine seismics to image the targets. The seismic data also clearly provides a new velocity model for the area, which can be used to process active seismic surface seismic data and improve the location of mining-induced seismic events to map seismogenic zones and mitigate geohazards. This is the surface data that we collected using the passive data. And also these experimental surveys are considered to be cost-effective, as the approach was approximately 60% cheaper than if the survey was acquired by commercial contractors on surface, keeping in mind the amount of time we took to conduct the survey, the equipment that we have used to conduct such experiments in underground environment. So now I'll quickly go through case study 2 as we are running out of time, where we were looking at characterizing water conduits and boulders using multi-geophysical methods. This is in an open pit mine where they have a problem of the pit flooding with water. And so our objective was to look at where does this water come from? Is it groundwater, or is it transported by fractures or dikes or any other geological structures? And also we look at the boulders. They have an issue of boulders where these boulders are causing issues for their blasting, but I'll discuss that in a bit. So the second site is an open pit, as I've already mentioned, but it's different to the first site because they are exploiting the middle group chromatites, and also some of the UG1 is being exploited in that area, and is also located in the western limb of the Bushveld, but in the Marikana section. And the main economic horizons, as I've mentioned, are the chromatite packages in the critical zone, which are the MG1, MG2, MG3, MG4, and UG1 also. Now, so for us to do this, we're targeting the boulders that occur on the subsurface, and they are so now as the mine operations advances towards the northern side, there is occurrence of boulders in the overburden, as you can see on this image, and these boulders can cause delays in production and machine breakdowns. It is quite difficult to fragment this area if we have these balls, and also looking into the water, as I've already mentioned, there is flooding of the mine pit. So our aim for this case study was to delineate the boulders and enhance mine planning and designs, detect faults and dikes that can be possible conduits for the water into the pit, and just characterize the near surface geological features, your joints, your fractures, and your weathered surface. So firstly, because we'll be looking at boulders and fractures and faults, we need to understand what causes seismic reflections and diffractions. And reflections most of the time are caused by the reflection energy due to vertical changes in elastic properties. When you have a plane reflector like that, you will be able to have your change in elastic properties in that direction. So you'll have a reflection going back to surface, while a diffraction is caused by lateral changes in your elastic properties. So for example, you have this layer here, but as you reach here, there is a fault that down throws that layer, and then you move into another layer, created this point diffractor here that will cause diffractions, and these diffractions appear as these hyperbolic events into your data set. So they appear as that. So since we are looking at faults and boulders and fractures, we should expect a lot of diffractions into our study. So the study areas, we had the west pit here and the east pit of the mine, where the west pit is where we're looking at the boulders, and the east pit, that's where we're looking at the water that is flooding into the pit. So now the geophysical methods and hydrogeological methods that we've conducted was magnetics. We had magnetics with us. We conducted seismics. We conducted multi-channel analysis, surface waves. We had resistivity, GPR, and we sampled some of the water in the mine. So to start off with magnetics, you need to, when you are collecting magnetics data, one is to carefully collect the data and do data quality checks and inspection of any possible sources of noise. We had encounters where there is a wire, it can be in any clothing, and this will introduce some sort of noise into your data set. So you need to carefully inspect anything that you will be having on your body when collecting your magnetics data. And also power lines can introduce electrical noise into your data set, so you need to also look into that. We also had resistivity. With resistivity, we collected a couple of profiles, and seismics also. We were on surface, so we were able to mount our weight drop onto the car and not use the sledgehammer, but there were other regions where we used the sledgehammer. We used both the lens streamer and the conventional spiked geophones for this seismic studies. GPR, we have our radiogram that we use, GSSI GPR that we use to collect our GPR data. Multi-channel analysis is one method that we just going into, looking into this surface wave technique that we use to map the shallow subsurface of the first top 10 meters to about 30 meters. And the technique maps the shallow subsurface with a high resolution and has the ability to map our ore bodies or bodies of low seismic velocities that are overlaid by bodies of high seismic velocity. So looking at our magnetics data, this is our data that we collected on the boulder site. And we can see areas of high magnetics and low magnetics. And we have this concentrated region here, which is a high magnetic low, which might be due to remnant magnetization. And then we have this high magnetic areas which are attributed to being the boulders that we're looking for. Magnetics shows delineation of norite boulders as high magnetic anomalies within the weathered host rock of the region. So we applied some processing on the magnetics data. We reduced PO, which will show us some remnants and repositioning of our anomalies. We applied some tilt derivative, which is more effective to image edges and fractures, as you can see them here. It's able to show us the edges and fractures. And then we also just have the total magnetic intensity shading, which also can show us our fractures in that region. We also conducted 3D model for the magnetics data, where you need to keep in mind that this is a susceptibility model, not a magnetic intensity data. And since it is a scalar, it is only defined by magnitude. And the anomaly at the center is associated with an IRAM. A linear color scale was used to display this model because it shows the biasness of the inversion to the anomaly with the highest amplitude magnitude being highlighted, which is the IRAP. And due to this bias towards mapping high magnetic anomalies, this model did not map the boulders. But as we remove the background data, we are able to see this small magnetic highs that exist in here, which we can attribute them to the boulders that we are trying to investigate. And then moving to resistivity, we are able to image our bedrock easily and also see these high resistivity regions which correspond with the surface boulders that we could actually see on the ground. The resistivity profiles show the norite bedrock, the weathered norites, which host the boulders that we're able to image on the resistivity profiles. And we conducted seismic tomography, which we are able to identify areas of low velocities, which are weak zones, which we can attribute this to fractures that exist within the host rock. And also we are able to image the top layer, which is the weathered, and then the fresh bedrock also. We are also able to see some sense of high velocity regions, which can be attributed to the boulders that are also fractured in some regions. There is a low velocity in between those regions, so we can attribute this to be the boulders that we are trying to image. You can see them clearly here, where you have your high velocity regions being isolated, which can be attributed to our fresh boulders that exist. Even the fractures are also clearly, you can see on the other line also the fractures are mapped properly and the high velocity regions are also shown. And moving to the GPR, as I've already mentioned, GPR is good at looking at diffractions. So on the data side, we'll be looking at these hyperboles that cause diffractions that might be due to point reflectors or edges of faults or dikes or any lateral changes. So on our data set, we are able to identify diffractions that correspond to those resistivity boulders that we have identified in the resistivity data, which increases our confidence in that study that we are able to image those boulders, which will assist us in identifying where these boulders are and help improve the mine blasting planning. So moving to the water conduits stuff, we conducted multiple magnetic data sets. We acquired multiple magnetic data sets, which you can see here. We have patch 1, patch 2, and patch 3, which were along the bench of the open pit, where we are trying to look at if we can image any sort of fracturing or faulting along. We also have this green line here, which is the dike that cross-cuts the pit, which we conducted magnetics on top of it. We also conducted resistivity and seismics just across the dike and the fault system. So looking at the first patch, we are able to identify the fracture system that trends southwest, northeast, which are associated with the dike mapped in the mine, and the edges of the dike give us a magnetic signature. Therefore, we were confident that we would image the dike at other areas. So this was to give us ground truthing because we knew that the dike is in that position. So we conducted a seismic, a magnetic survey in that region to do some ground truthing. So looking at the resistivity profile, the profile crosses the mapped fault, which is represented by blue here in the mine. Therefore, we are also confident that the resistivity will be able to image any fracture systems that are in the mine pit. As you can see here, there is a high resistivity region that is disturbed. And also moving to the seismics, we are able to see some displacement of this reflection here, which corresponds to the same fault that was seen on the resistivity data set. So the MASW was a pilot study for this site into using, we were testing this method for tailing dam monitoring to check if there is any seepage of water along the side of the tailings dam. So this was compared with the resistivity data that was collected along the same region. And as you can see, those regions that correspond there, this low velocity that goes there. Then we also had the broadband seismometers as in the previous case study that we had. But we had the broadband seismometers collect data set for about 35 to 36 days in this area. And record any local seismic background noise, earthquakes, and blasting that could be happening in that region. So this is an example of a seismic event from blasts with a local magnitude 2.4, which happened, they were blasting in the pit, as you can see here. So we are able to identify those blasts. And then we have some of the events that happened all over the region. As you can see them here, we are able to locate where this any movement happened in those days that we were collecting this data set. So looking at those and the broadband data, we were also able to record data that is very far from the mine, as the study was happening in this region, and we also had events that happened in areas like the Fredderford, which is more than 150 kilometers away from our study area, even in the Tabazimbi region, which there is mining in that region, so that might be due to that. And also the Krugersdorp, Potchefstroom, which we have gold mines in that site. So the seismic events might be caused by blasting in those regions. So the fracture networks and dikes in the pit, we were looking into water sampling water from the river that cuts through the two pits and also the tailings dams areas where they stored water, any borehole data, and any borehole sampling that we have to be able to do some isotope analysis for that. So we collected this water sample around the mine and conducted as an isotope analysis, as I've mentioned, and some source points display a mixing signature, and the mixing may occur due to fractures or fault activity bringing water into from depth to the surface, where it may mix with the water infiltrating from the dewatered areas of high elevation. Some of these display minor evaporation from the bulk groundwater, which is possibly due to the pumping of water back into the pit, meaning that there is some recycling of the water into the pit due to through the dike and some of the faults that exist in this region. So in summary, our results indicate that the application of integrated high-resolution geophysical surveys should be recognized as a core exploration mines for near-surface characterization and delineation of boulders, dikes, and fractures to enhance mine planning and designs. Seismics and electrical resistivity were particularly successful at mapping the depth to the topsoil, the weathered zones, and the fresh bedrock. The results from the isotope analysis assist in identifying the source of the water. So what is next for us is the fiber optic sensing and UAV platform techniques for innovative mineral exploration, which is future, where we'll be looking at using surface borehole tunnel seismic solutions to image our ore bodies, which the project is kicking off this year. It's called Future. And this is an exciting project that will be bringing the different state-of-the-art equipment into the country, like the electrical source, the GPS time transmitter that we had issues with, and all sorts of other cabled sensors, lens streamers, and the wireless nodes that we'll be doing. So this, all those will enable us to conduct the seismic experiments in underground and so synchronize this wireless sensors with surface sensors also, and be able to image any geological structures between the tunnels and the surface, and also below the tunnels. Thanks to the Seismic Research Center for this opportunity, and also the 2 mine sites for giving us access to the mine, and also the AOK program under the MMP for supporting this project, and all the VETS postgraduate students for that. And any questions from here? And yeah, thanks for listening, guys.
Thank you so much, Kenneth. Your presentation was very clear and nice. I just want to ask if any of the audience, if you have any question, you can either type it in the chat box or unmute yourself and ask Kenneth yourself. Okay, I guess we do not have any question now. So we have come to the end of this meeting. I just want to say thank you so much, Kenneth, for honoring our invitation. I will have put on my video now, but the network is very poor. We have the rain is falling. So I want to thank all the participants also. Thank you so much for joining. We hope to see you next in our meeting.
All right, no problem. Thank you.
All right, thank you. Bye.